Right. I'm Professor Gary Bernstein at the University of Notre Dame, Department of Electrical Engineering. This is a very informal video just to introduce students to an oscilloscope. And I think it's most informative to start with an old style analog oscilloscope. They still make them, but in the class you'll be using a digital oscilloscope. So I've set this up to have an input to this oscilloscope of a sine wave of very low frequency. You can see right here that this is a sine wave and its frequency is 1 hertz. 1 hertz means it does 1 cycle every second, and when you look back here, it's tracing out a sine wave. It's tracing out a sine wave that is going at about once per second. Now what you're looking at is an electron beam glowing on the surface of the screen, the phosphor, and there's a horizontal ramp generator that's causing the beam to move across the screen. The vertical axis is like a voltmeter. It's saying at every instant in time, this is the voltage. So it's tracing out a sinusoidal voltage as a function of time. First of all, let me change the frequency over here. And as I increase the frequency, you can see that it goes up and down faster because I've increased the frequency. Now I'll decrease the frequency. So you can see that I can change the frequency of the generator. Now let's go back to the oscilloscope, because after all this is about oscilloscopes. This knob changes the speed at which the beam moves across. I can move the beam more slowly. Well, not there. This is the slowest it can move across. There it is. It's traveling this way very slowly. I can make it move a little faster. See that? I can make it move even faster and faster and faster and faster until it just looks like a line. Now it just looks like it's going up and down sinusoidally, but it's really the same wave that we started with. It just changed the horizontal sweep frequency. Let's go back to a fast sweep. And now I'm going to increase the frequency of the generator. So we're at 1 hertz. Now show it right here. And I go to 3 hertz, 3 times per second. Now it's 6 times per second. And now it's going 15 times per second. Let me, and now I can change the sweep frequency so it's even faster. Or, yes. So now it's sweeping at 10 milliseconds per division, and you can see again that it's a sine wave, but it's higher frequency. I'm going to change it even more, a higher frequency yet. And look at that. As we increase the frequency, we get more sine wave periods per unit time. So as I increase it, there will be more and more of these on the screen, and you can see that there are in fact more showing up on the screen as I increase the frequency. So now we're at a frequency of about 150 hertz. Now if I want to look at this, I can change the time base to go even faster. Now what happens when you increase the time base speed, what you're doing is you're making it go more quickly. We get fewer number of periods on the screen at any instant in time. So here we are, and I make it go more slowly. We get more periods, make it go faster, and we get fewer periods. So I want to demonstrate something called triggering. Right now this is an old scope. It's having trouble triggering. Now this looks like it's floating across the screen because the oscilloscope is selecting a very slightly different time to start the trace each time. If it selects exactly the same time for the trace each time, and it's not a very good scope apparently. Let's do this. There. It's triggered. The reason it looks like it's not moving is because this oscilloscope is triggering at exactly the same point. So it triggers and it makes a trace, It stops, it comes back, it triggers and it makes a trace, and it repeats that frequently so that it looks like it's not moving. It's synchronized. Now we already saw from having a really low time base that there's almost no persistence to the screen. The only reason that it looks like it's staying still is because it's happening many, many times a second. Okay, so this is an analog oscilloscope. And by the way, I can change the amplitude, which says that I have more volts per division and that I have fewer volts per division. So I can increase the size and I can decrease the size. This is called, I don't know what I just did, but that's called the vertical trace. What just happened? I think I must have pressed something. What's going on? It's just an old junky oscilloscope. There we go. It's not very good quality. So anyway, I said this is going to be informal, and I meant it. Anyway, so as we change the amplitude, we can see more or fewer volts per division on the screen. All right, this is an old analog scope, and that demonstrates the movement of the CRT. Now, a digital oscilloscope, which is right here, which we're going to demonstrate in the next video, does not have a moving, you can show me, it does not have a moving electron beam. At every point of the trace, an analog to digital converter saves the voltage, stores it in memory, and then later on, an instant later, it shows it on the display of the screen as if it's a computer screen. So modern computer screens that are LCD displays, they don't have a moving electron beam. So it's completely computer-based, and that's why it's called a digital oscilloscope. Okay, so that's it for now. When I come back on the next video, I'm going to introduce the waveform generator in some more detail, and then show you the oscilloscope and show the basic operation of the oscilloscope.